So as we get started on the Chapter 6 review, let's just get into number 1. So what they want us to do is consider the experiment of tossing a pair of 6-sided dice. Find the probability the sum of the numbers that are face up is at least 9. So you're going to toss die 1 and die 2. They both have 6 options to happen. That means there's 36 in the entire sample space, which is right here. And they want us to find all of the 36, what's the probability they have at least 9. And at least 9 would be all of these right here, which will give us a total of 10. So for number 1, the probability is going to be 10 out of 36. Don't forget to simplify that to 5 out of 18 is the answer for that. Okay, the second problem, a fair spinner with 6 congruent sectors numbered 1 through 6 is spun twice. So we have spin 1 and spin 2, 6 sectors on one, 6 on the next, so 36 outcomes. And I'm going to keep the sample space here of the 2 dice because it's a very similar sample space, except it's the face of a spinner. Here's a question. What is the probability that the first spin is a 4 or the second spin is an odd number? So probability the first equals a 4 or the second is odd. What we want to do with an OR probability is add. So the probability that the first is a 4 plus add to it the probability that the second is odd. But don't forget to subtract out any cases where both happen, where there's overlap. The first is a 4 and at the same time the second is odd. So as you look through this sample space, the probability that the first one is a 4, if you take a look at it, we're going to have these right here. That's 6 out of 36. Add to it the probability that the second number is an odd. The second is going to be odd, is either going to be here in this case with the 5, the 3s, or the 1s. That's actually 18 out of 36. And then we subtract out any of those that we have where the first is a 4 and the second is odd, and you're going to see that you do have some overlap on that in the case that 3 of them. When you simplify this answer, we're going to get 21 over 36. You can actually factor out a 3 of that, so what you'll get is 7/12 is the correct answer. Now there's a second way you could have looked at this problem. You don't have to do it 2 different ways, but do let me show you. What you could have said is for this one here, what's the probability that the first spinner is a 4? That's the same as just having 1 out of 6, by the way, because it's just looking at one spinner. What's the probability the second spinner is an odd number? That would be 3 out of the 6 numbers are odd. But then this would be the same thing. The probability the first is a 4 and second is an odd would still be 3 out of 36. So then what you would do is just get a common denominator for these 3 fractions, and you'll end up getting this exact same answer. So you can look at the entire sample space like I did in the first one where I got all fractions of 36, or you can think of it in other simple terms, but just get a common denominator for that. Okay, our next problem is number 3. How many 4-letter permutations can be made from the letters in the word hospital? You're going to notice the word hospital actually has 8 letters in it. So from here, hospital has 8, and I want a 4-letter permutation. So I could do the product of integers, and I want 4 letters. Hospital has 8, and I have 8 choices, then 7, 6, and then 5. This will multiply into giving me 1,680 different choices. Keep it in mind, a permutation means no repeat. So if I go in the hat and I pull out the letter S, I know that would be my first choice of 8. The S is no longer there. I'm down to 7. Okay. Another way you could do the permutation, you could say it's 8, choose 4. In your calculator, you would type 8, then NPR button, and then 4, and you'll get the same answer for that. Now number 4 is a slight variation. How many 4-letter permutations, again, no repeats of our letters, can be made from the letters in the word hospital which contain no P? So the P is no longer there, which means we only have 7 choices. So I'm going to make a 4-letter word again. With 7 choices, I put my hand in. There's 7 to choose from. then 6, 5, and 4. That's the same as saying 7, choose 4. And what we get for an answer on that one is going to be 840. Number 4 wants us to evaluate 10, choose 4. Two ways you can do this. You would say I have 10 and I'm going to choose 4 spaces. If there's 10 items in a hat, you're going to pull out from 10 choices, put something down. You do not replace it. That's what a permutation means. So then we have 9, 8, and 7 left. You can also do the formula for this, which would say it is going to be 10 factorial over 10 minus 4 factorial. That's 10 factorial over 6 factorial. This actually simplifies to 10 factorial all the way down to 1, and then 6 factorial all the way down to 1. So what you're ultimately going to be left with is this will all cross out, and you're just going to have 10, 9, 8, and 7 left. So the answer for number 5 is going to come back to being 5,040 is what 10 choose 4 equals. Now what does it mean? It just means that, again, you could say you have 10 slips of paper in a hat, you have 10 marbles in a hat, what have you. You're going to choose 4 of them. Okay, if we look at number 7, A and B are two events in an experiment where probability of A is 0.5 and probability of A and B happening is 0.2. Find the probability that B happens given that A happens. This is a conditional probability from section 6. And again, what it means, it's like a sideways fraction. So what you would write it as probability of B given A means this A part is on the bottom. So they want the probability of A. So we are actually not looking at a complete population, but just a part of a population. And then the probability of A and B happening. So these two events, all you want to do, the probability of A and B happening is 0.2. The probability of A happening is 0.5. This simplifies to 2/5 or 0.4 in terms of a probability. Now, number 8, if we take a look at that one, says A and B are mutually exclusive. You want to remember that mutually exclusive means they have nothing in common. Okay? If you have to find the probability of A is 0.6, B is 0.1, they want you to find the probability that not A or B happens. The best way to approach this would be of this nature. So what I would do is probability of not A or B, its complement, you could say probability of not A or B is the same as 1 minus the probability of A or B. So what you can do is just keep that as 1 minus and find the probability of A or B. That is the probability of A plus the probability of B. But then you would subtract out if A and B have anything in common. So from this, what we could write then, probability of A is 0.6, of B is 0.1. Probability of A and B having anything in common, they are mutually exclusive, so it can't exist. So that would be 0, by the way. So you're going to have 1 minus 0.7, so the probability in this case is going to be 0.3. Okay, we have here for number 9 and number 10, I bring this down, the case says this. Each of the whole numbers 1 to 8 is written on an index card and the cards are placed in a bag. A card is drawn from the bag, the numbers recorded, and then it's put back in the bag. The process is repeated, so there are a total of 6,600 cards drawn. When we look at this, by the way, what you're seeing is this total is the 6,600 of all the results. Number 9 asks you this. What is the expected number of times the number 5 will be drawn? Remember from section 6.8, expected number or expected count is take the number of experiments times the probability. So experiments in this case, as we did 6,600 experiments, the probability of randomly drawing a 5 from a group of index cards 1 through 8 would be 1 out of 8. So the expected count for this case would be 825. That is, you would expect to get about 825 cards. Okay. Looking at number 10, if these are the actual results of the experiment, what might you conclude about what's going on? Well, if you look at all these numbers, the results from number 5 really pops out. We would expect 825 cards to have been drawn, or roughly around that amount. It is by far exceeds it, so it looks like there's something happening to that number 5 card. Maybe it's larger than the others, it's something skewing it, so the odds of it being drawn are not as fair as the other cards, is what you could say. Now number 11 is extension of this. Could you decide if the 8 cards are equally likely to be drawn if 5 is drawn 4 times in the first 20 draws? So again, could you decide if of these 8 cards, are they all equally likely to be drawn if the 5 is drawn 4 times out of 20 draws? Well, if the 5 is drawn 4 times out of 20 draws, its relative frequency, 4 out of 20 is 1/5. Okay, so the relative frequency is what's happening in the experiment. However, the probability of it being drawn is 1/8. So you would look at that and say it's not really fair to know, because relative frequency, what we know about this, the law of large numbers says the more times you do an experiment, the closer the relative frequency will become to the probability. We've only done the experiment 20 times. We should do it at many, many more times. In this case, I did it 600 or 6,600 times to get a better understanding. So because the law of large numbers holds here, 20 draws is not enough draws. I don't know if the 5 is skewed somehow. The last problem on this page asks us this. A pair of 6-sided dice is rolled. Let A be the event a 6 is rolled on the first die, and let B be the event the sum of the numbers rolled is 10. Are A and B independent of each other? You want to remember the test for independence. It's this. Find the probability of A and times it by the probability of B. That means 2 fractions. Sorry, and I want B. Okay. So do that first. Okay, the probability of A happening. Event A is this. A 6 is rolled on the first die. If a 6 is rolled on the first die, you could think of it one of 2 ways. You could say it's 1 die, so it's 1 out of 6. Okay? Or you could say the 6 is rolled on the first die. If you get the whole set, it's 6 out of 36, which is the same as that. Okay? Probability of B. The sum of the numbers rolled is a 10. The sum of the numbers rolling being a 10 are going to happen as a 6-4, 5-5, and the 4-6 combination. So that's going to happen in 3 out of 36 cases. If you multiply these together, you'll get 1 out of 72. Now what you need to do is compare that to the probability of A and B happening at the same time. Notice the difference here. There's one P and there's another P. That means one fraction and a second fraction. Here I just find the probability once. They want one fraction. So I'm going to say the probability of A and B happening together is what? So do this. That a 6 is rolled on the first die, so it's this group right here. And at the same time, the sum of the numbers rolled is a 10. That happens 1 out of 36 times. So what you're going to do is compare this fraction and this fraction. They're not the same, therefore these 2 events are dependent on one another, which means the outcome of one will make an impact on the other event.